Alright, in this video we're going to talk about friction. Okay, so we've established setting up Newton's laws for different problems and using free body diagrams. Perhaps it's on a ramp. We talked about gravity a little bit, and so the next big force is this idea of friction. And so we've already kind of mentioned this before, so let's just hit the immediate basics of this. So friction is simply a resistive force. Okay, and that's important because when you're making your free body diagrams, just remember that friction can never point in the direction of motion. Okay, it's always against the movement. Always against the movement. Okay. So the other thing we can do with friction is friction comes in multiple forms. Okay, and so the two that we're going to really focus on the most for sliding friction, well, let's do it that way. Let's say two different kinds. So we have a sliding friction, okay, and we also have like air friction. Okay, so for sliding friction we have two basic types. You have static and kinetic. And then for air friction, well, that's what we're going to, that'll be the second part of the video where we talk about drag forces and different types of air resistance. Okay, so let's focus first on the sliding friction part. All right, so we'll start with static. Now, so static is essentially not moving. Okay, we've already kind of talked about that with equilibrium, right? We had a static equilibrium, meaning that the object was not moving and all the forces were balanced. Well, static friction is the same idea in terms of it's not moving, and it's a friction caused by objects, by forces trying to move stationary objects. So imagine we have a box, okay, of some mass. Let's say the mass is 10 kilograms. Okay. And if you were to walk up to the box and you applied a force, right? Let's say we tried pulling this box with, say, 200 newtons of force. Okay, and we'll say that the box does not move. Okay, so the question is, well, if I try to pull on the box and it's not moving, then that implies that there must be a frictional force resisting you, such that when I make the free body diagram, okay, we've got 200 newtons in one direction and a friction in the other direction, and these forces would balance because the object's not moving. And since these forces balance, we can conclude that this must be a static friction, which is why we label it with an S. Okay, and then if you were to have moving friction, so if you had kinetic friction, okay, this time you could have the same setup where you tug on it with a force, and we'll do the same thing. We'll say 200 newtons of force, and in this case, multiple different things can happen. Okay, you've got a kinetic friction in the back, and since it's kinetic friction, we can conclude that the object is either moving with constant speed, because in that case the net force would still be 0, right? So if F net was 0 here, it's moving with constant speed. And we know it's moving because we're using kinetic friction. Okay, and then of course there's the F net is not equal to 0, and that would mean one of these forces is much bigger than the other. If the applied force is bigger, then the object would have a net acceleration and therefore be speeding up. If the kinetic friction was bigger, then you would have a net acceleration in the opposite direction, in which case the object would be slowing down. Okay, so that's the visual of how these two frictions differ. So what I want to do now then is let's go back to static, and this time let's put a little more quantitative analysis to it. So for static friction, we have a formula to determine how much friction occurs. Okay, so static friction is described as an inequality where the static friction force, so the Fs represents the amount of friction acting on an object, is always less than or equal to the product of what we call the coefficient times the normal force. Okay, so the coefficient, what that basically is it's a number that is a property of the two materials in contact. So it's a property of the materials in contact. Okay, so this coefficient number can change depending on the type of materials. You'll never have to memorize a certain type. It's always referenced or provided, or it's what you're trying to solve for. Okay, and then Fn, of course, is normal force. Now, the reason why it's less than or equal to is, let's go back to our picture. And so here we've got the box. We'll say it has a mass of 10 kilograms. Okay, we'll say it has a static coefficient of 0.8. Okay, and now I am going to apply force, we'll say of 50 newtons to the right, and the object does not move. So somewhere up here we would say the velocity is 0, it's not moving. So it means that there must be a friction force, a static friction force, fighting against me. Now, how much is that static friction? Well, if I use the formula, if I were to say that static friction, the static friction is equal to the coefficient times the normal force. Okay, first, in order to figure out the normal force, if we look at a free body diagram, normal force is straight up, force due to gravity is downward. We had 50 newtons to the right, and friction to the left. So if we look at the vertical line, we see that the normal force is balancing out with gravity. So that's simply equal to mass times gravity. So that means our static friction then is equal to the coefficient, which is 0.8, times the normal force, which is mass times gravity. Okay, and again, it's 9.8, but I'm just going to round it up to 10 here. So it's 100 times 0.8, which would mean static friction is 80 newtons. Okay, now there's a problem here. We didn't do the math wrong, and yes, the static friction equals up to 80 newtons, but there's a reason why our original formula had an inequality. And that reason is, if static friction was 80 newtons, then when I look along this horizontal line in my diagram, here's the problem. I've got 50 newtons minus friction, and I'm saying that because it's static, it shouldn't be moving. Therefore, the net force should be 0. But when I do 50 newtons minus 80 newtons, that definitely does not equal 0. So something happened there. Okay, and it turns out that what we found by applying this formula, what we found is that this is the maximum amount of static friction. Okay, and that's what the inequality is for. Again, static friction can be less than or equal to that product. So in this case, the static friction would have to be less. If I want this formula to work, to say that it's balanced, it follows that friction must only be 50 newtons. Okay? And then what the maximum friction allows us to do is to figure out, well, if I applied, same box, say this time I apply 80 newtons to the right, well, let's go above that. We'll say I apply 100 newtons to the right. What's that going to do to this box? So we have the same basic forces, but this time, because I'm applying more force than the maximum amount of force allows, this means that we have broken static friction's hold. Okay, so in other words, static friction is too weak to hold the object at rest. And so now the object moves. Okay, and so now friction becomes kinetic. Because now we're moving. And once we're moving, we haven't changed the fact that there is friction, but now it's a kinetic friction. Okay, and an example of this would be, imagine like you're trying to move a refrigerator on carpet. So if I had carpet here, and we've got a very massive object on that carpet. If you try to move this, right, you're going to apply a force that doesn't do anything. It doesn't move. You've got friction fighting you. Okay, and then I push with a little more force, still doesn't move, and then I finally push with a much greater force, and then the object starts to move. Okay, and then once I have the object moving, okay, so in other words, if I make this into another picture, once the object is moving, okay, I can now apply a smaller force to keep it moving. Okay, and the reason for that is because in the picture on the left, when we were in static friction, picture on the right, we're in kinetic friction. Okay, it turns out that the static coefficient is always bigger than the kinetic friction. Okay, and all that means is it takes more force to get an object to start moving than it does to keep an object moving. So one of the things you're going to do is you're going to do a lab this week, okay, where we're going to look at how much applied force we apply over time to an object. Okay, so you've got this object sitting here. It's got some mass to it, and so since it has mass, we know gravity's going to tug on it downward. It's touching a surface, so it's going to have a normal force. We are going to apply a force in one direction, and as a result, we know that there's going to be some amount of friction fighting back on us, and it's going to be both static and kinetic friction, because first it's not going to move, then it will start moving. Okay, and when you graph it, what you're going to see is this force over time. We're going to gradually pull with more and more and more and more force until it spikes on us. Okay, and then after it spikes, you're going to see it drop down and level out. Okay, now what that means is that when it got to that spike, the point is, in this window, the object was not moving. And you had to pull harder and harder and harder on the object to make it move. And then when you've reached this peak, that value represents the maximum static friction value. Okay, it was when you finally pulled with enough force to get the object to move. Okay, and then after that, you can notice that suddenly your force dropped off. Okay, so that means that for this window, the object is now moving. Okay, and once the object starts moving, the force drops off and then levels off. And the reason why is because that amount of force, okay, represents the kinetic friction acting on the object. And we know that that's the kinetic friction because if your force stayed constant, okay, and the idea was this is moving eventually with constant speed, then it follows that the applied force must be equal to the kinetic friction, because if it's balanced but moving, then it's moving at a constant speed. Okay, and so you can use that type of analysis to figure out what the coefficients are between the objects. But again, you see that I have to apply a lot more force to get it to start moving, and then once it's moving, it'll move off with a constant speed. And that is because the static coefficient is always greater than the kinetic. Okay, now let's do an example with air resistance. So we said the other type was an air friction. So in this case, it's considered air resistance. Okay, so if I've got an object, say, a ball and it's falling, okay, in the absence of air resistance, it's only gravity pulling it down. But with air resistance, we're going to have this drag force applied up to it. Okay, and the thing about a drag force is that it's always dependent on the velocity. Okay, the faster I move through air, the more friction, the more air resistance applies to the object. Okay, you can imagine like when you're in a car. You put your hand out in the parking lot as the car is moving very slowly. You can feel the wind, but it's not applying a lot of force on you. Then put your hand outside the window when you're going 50 miles an hour down the road, and you're going to feel that air really hitting your hand. Okay, and that's the example. The faster I go through air, the more resistance it pushes on me. So that's why we say it's dependent on the velocity. Okay, so in your book, they give you a very complicated formula. Okay, and what we'll basically do, and the way the AP exam wants you to see it, is they always give it to you in terms of either a constant times the velocity squared, or a constant times the velocity. Okay, and the negative sign is just like all that represents is that it's resistive. Okay, and so the B, the letter B, is a constant, and when you look in the book, it's like a 1/2 times a constant for the air composition times the surface area with the mass, and there's a lot of other things that factor in air resistance, right? There's a reason why a bowling ball can fall through the air with less air resistance than a piece of paper. And all those properties get factored into the letter B for what the AP exam wants you to do. So we're going to kind of follow that same format. Okay, so when I've got air friction acting on this object, when I set up Newton's second law, okay, the idea is we would set this up just as we would any other problem. You've got the drag force and gravity is equal to ma. Okay, keep in mind everything's a vector. Okay, and so when we apply the drag force, okay, in this case we said the drag force is negative bv, and for gravity we'll say it's also negative mg equals ma. Now this should make sense mathematically, because if it's falling downward, then v is negative, which will make this overall force positive. Okay, so that's why that negative sign's out there. Now when we set this up, I mean, this is a very simple setup, but in physics C, in basic physics, what we want to refer to this as is using Newton's second law is always referred to as the equation of motion. Okay, if you're looking at a problem and it says, what is the equation of motion? It means start from Newton's second law. Okay, and then sometimes it'll also say, it'll add in a differential equation of motion. Okay, and what differential means is it's an equation with derivatives in it. Okay, so in the case of this example, if I want to write out air resistance as a differential equation, okay, that means we want to put it in terms of the same variable. Okay, for example, v is a derivative of position, but a is a derivative of velocity. Okay, and if we want to make this easier on ourselves, we can also say that this is the second derivative of position, but we don't want to have to deal with multiple derivatives, multiple layers of derivatives if we don't have to. So rather than referring to position derivatives, we can put acceleration in terms of the derivative of velocity. Now we have like variables, whether it's velocity and the derivative of velocity. So that means we take this equation and we rewrite it to say negative b times v minus mg is equal to the mass times the derivative of velocity. Okay, and we could do some math here and divide out the m and end up with an equation that says minus b over m times v minus g equals dv over dt. And there would be a differential equation describing the motion of the object. This is really, again, look back where we started, net force. This is Newton's second law in differential form. And with this, we can actually try to solve something. Okay? Now, the calculus of this can be a little tricky since most of us haven't had the calculus we need to do this yet. But for right now, the big idea is, well, what happens over enough time? Okay, as you could see in the equation of motion, since the drag force is dependent on velocity, so since drag depends on velocity, okay, that means the faster you go, the more drag. Okay, now we've already kind of said this, but here's the important part to grab from that. Eventually, something's going to happen. At first, I have a lot of gravity and almost no drag. Okay, and then over time, the gravitational force doesn't change, but I'm going faster because my acceleration, the net acceleration, is down. So I'm going faster and faster and faster downwards. That means my drag force is getting larger and larger and larger. And eventually, it'll get to a point where it's exactly equal to the friction, and when that with the gravity, and when that happens, the net force is zero. And when the net force is zero, since I'm moving, that means it's now moving at a constant speed. Okay. Now it's important to understand that the drag force will never go greater than gravity in terms of how we solve the problems. Now, if you had someone like jumping out of an airplane, this would happen. The drag force would increase and increase. And then if they were to open a parachute, well, in that instant, the drag force becomes a lot greater than gravity, which is why the person moves up a little bit because they slow down drastically. Okay, they're still falling, but if you were falling next to them, they would appear to move upwards because their drag force got a lot bigger instantaneously. But even once it gets bigger, for that instant, once they become balanced out again, they remain that way. And when this happens, we refer to this situation as terminal speed. Okay, it's when the net forces have canceled and you're now falling at a constant speed because drag and gravity are canceling each other out. Okay, so if we go back to our equation of motion that we had, so in the case we had minus b over mv minus mg equals dv over dt, and we want to find the terminal velocity. Okay, that means the velocity is no longer changing because we're moving at a constant speed, so the dv dt is 0. And then we're simply just going to, oops, sorry, there shouldn't be an m there. We canceled out the m. Okay, so I'm just going to solve this for v. So we add the g over, multiply by the inverse of b over m, so we get mg over b. And this would represent the terminal velocity. Okay, and of course, if you remember, I said drag force can be two things. It can be bv or bv squared. You could also have done this with bv squared and just did one extra step and do the square root. Now, of course, it's negative because it's falling. So when we fall, the terminal velocity is going to be downward. Okay, if we said terminal speed, we would just truncate off that negative sign. Okay, and that's the idea of finding terminal speed. Okay, now I'm going to go through and do this one example of how you would actually solve this out. What if it wasn't at terminal velocity? Okay, how do we actually find the equation for velocity for this falling object? So now we're going to actually do the calculus. Okay, and so one of the processes you're going to use for this is known as separation of variables, because since there is a v and a t, I mean in this case it's a 1 on the other side, but since there's two variables v and t, we need to separate the v's and t's so that we can take an antiderivative of each variable separately. Okay, and so because the v is not attached to the dv initially, you can see it there on the left side, we have to move that whole expression over to the other side. And the only way to do that is to divide off the whole thing. So we got b over mv plus g times dv over dt. So we've moved the v over to one side. Now we got to move everything with t. So in this case, that's dt to both sides. Okay. Once we do that, we've got negative dt equals 1 over b over m v plus g times the derivative of the velocity. So now we've got everything separated because b, m, and g are all constants, so it really doesn't matter where they are, but they're attached to the v. They have to move with it. So now we're going to take antiderivatives of both sides. Okay, so on the left side, that should be easy. The antiderivative, negative dt, is just negative t plus a constant. Now on the v side, you'll have to look back at some special function derivatives because the only way a derivative of a variable ends up with the variable on the bottom is when you do a natural log derivative. So in this case, it would be the natural log of all the stuff that ended up on the bottom. Okay, and because there's a chain rule aspect of this, when you take a derivative, the chain rule derivative with respect to v pulls out a b over m. So in order to cancel that b over m, there had to be an m over b on the outside. And then, of course, plus a constant. Okay, now, we don't know what these two constants are. They're not the same, or may not be the same. So if I want to move this over to the other side, again, I don't know if they'll cancel because they may not be the same numbers. But I know that when I combine them, what I end up with is just simply a new constant. Okay, so I can do that. That gets rid of the constant on one side. Okay. Now, if I need to get an expression for v, I have to get it out of the ln. So in order to do that, I need to get everything off of ln. So let me move the m over b to the other side. Oops. So that cancels it off here on the right. And on the left side, that gives me negative b over m t. And then b over m is a constant times another constant is still a constant. So now I got ln of b over mv plus g. Okay, now in order to get rid of the ln, the trick is you need to put an e to both sides, basically raise the two sides of the equation as a power of e, and that'll cancel off the ln. Okay, so let's start it on a new page. So on one side, on the left side, I will have e to the negative b over mt plus c. And on the right side, the ln goes away. All right. Now we can do some algebra here to get rid of the g, or sorry, to get rid of the stuff and get v by itself. One of the first things we could do is fix the left side. Okay, property of exponents. Since it's the same base and adding two exponents, we're really doing negative b over mt times e to the c. Well, e is a constant, and so is c. So a constant raised to another constant is just a constant times e to the negative b over mt. Okay, then we're going to subtract g to both sides. Okay, and then we're going to move the m over b. So we multiply, sorry, we move b over m. So I multiply the whole thing by m over b. So on the right side, I've got v. On the left side, m over b times c is just another constant. Okay, and then I multiply that here, and I got minus mg over b. So now I have an expression for v. That's not quite good enough because I need to know the constant c. So a typical starting point would be if this object came out of an airplane, for example, or whatever. Typically, the velocity is 0 when the object starts moving. It's like it's being dropped. So if that's true, then that would mean that c times e to the 0 power minus mg over b is equal to 0, and that means that c is equal to mg over b. All right, so that means our final equation for velocity as a function of time is mg over b times e to the negative b over m times t minus 1. Okay, and so there's our expression for an object falling with air resistance. Okay, and it is a long process to solve these out every single time. Most of the AP questions don't really even award you many points for doing all that mathematics. Okay, and so, but what you need to get from this is the function itself and what it looks like if you were to graph it. Okay, as it turns out, if I were to graph the velocity with time of an object like this, the object starts at rest, and then as it falls, it starts off with a high velocity, but eventually will level out. Okay, and the reason it levels out is because, again, that's where drag force is starting to take over. And so this represents the terminal speed, or terminal velocity. Okay, and in a lot of cases on these problems, they're going to ask you to do a couple things. They're going to do, one, set up the equation of motion, which we did. They're going to ask you to find the terminal speed, which we did. They're going to ask you to set up a differential equation to describe the motion, which we did. Then they're going to ask you for some graphs to show what it looks like. Like, what is the actual falling of an object in air resistant look like? And that's where we get this graph from. Okay, then usually the last part, if it's even there, will say to find an expression for v, and it's usually worth the least amount of points. So if the calculus screwed you up here, don't worry about it. But you can put yourself in a place where you know the velocity has this e to the negative constant times t function, and that'll kind of give away, especially if it's multiple choice, what the actual expression is. More importantly, it helps us describe the graph. Okay, the only other thing would be that if they wanted a graph of terminal speed, or not terminal speed, but a graph of speed versus time, and that's typically the question that they ask you, because you know, I could have picked my coordinate system different than you, which makes my graph go negative and yours go positive. So when they say speed, it's because they want everyone to graph the same thing. So just keep in mind that speed is it's no longer a negative velocity, so we remove the negative, and so our graph would look the exact same, except that it would be a positive graph instead of negative. Okay, where this line is still representative of the terminal speed.